We're putting together a simple optical system in order to produce a parallel beam of light. There's a circular aperture in this light shield. George is placing a carbon arc behind it. The arc approximates a point source of light. The fluorescent solution in this glass tank shows a divergent beam. But, as I've told you, we want a parallel beam. George is introducing a collimating lens. A second lens focuses the light on a little screen. It's the image of the brightly lit circular hole in the light shield. The beam between here and here is still parallel. This is a red filter. It passes only a narrow band of red wavelengths. The red image on the screen is, of course, far less intense. Between these 2 points, the beam is monochromatic. I'm putting a glass prism into the beam. The red spot disappears because it has been refracted by the prism. It is bent away through quite a large angle. We are now looking at a trace of the beam from above. The light beam is refracted as it enters glass. It is bent toward the line which is normal to the glass surface. We hope that you have heard before of Snell's law, which governs this phenomenon, and how this law can be derived from 2 important assumptions. These are, first, that light is a wave motion, and second, that its speed is less inside the glass than outside. In this film, we are not concerned with the simple derivation of the law of refraction. Rather, we ask the question, why is the speed of light less in glass than outside? Why does the glass prism slow red light down? As we look for an answer to this, we'll continue to assume that light is a wave. To be precise, an electromagnetic wave. So, I want you to think of a single monochromatic light beam, a sinusoidal wave of given frequency. By its speed, I mean the speed with which its phase advances. This is the so-called phase velocity. In free space, it has the value 3 times 10 to the 8 meters per second, and it's usually denoted by the letter c. The speed of light in free space is the same for all frequencies. This isn't true, you know, when light passes through matter. The phase velocity of light in a given material can be different for different frequencies. And what's more, it can even be larger than c for some frequencies. All this is possible because of the way the atoms and molecules of the material react to the light as it passes over them. So, to begin our classical theory of refraction, let us think first of empty space. Then, of a light wave coming at us through the empty space with speed c. We plan to fill the outlined part of space with a material, such as glass or another dielectric. We shall think of it in successive molecular layers and have indicated the first layer. Let's concentrate on this layer. The incident electromagnetic field oscillates as the light wave passes over the layer. The vertical oscillating vector is the electric field. It causes the electric charges in the molecules to oscillate up and down, the positive charges one way, the negative charges oppositely. The 2 kinds of charge are separated. The electric field creates oscillating molecular dipole moments. Now, the magnetic field, which oscillates horizontally here, also exerts a force on the moving charges in the molecules. But this force is small because the speed v of the moving charges is very small compared to c. We can neglect its effect in our discussions. Notice that we chose to let the molecular dipoles oscillate in phase with the incident wave. We don't really know why they should be in phase. At this point, let's just assume that the molecular oscillators respond in phase. We'll prove to you that this leads to a slowing down of the light, which will explain the bending of red light toward the normal as it enters glass. What is important to us now is to realize that the oscillating dipoles will radiate. Each will send out its own little electromagnetic dipole wave, which will spread from it in all directions. We want to know their effect at forward points. Any point, such as the one marked P, will receive a small signal from each of these dipoles. In addition, of course, the incident wave will get through to P. For instance, consider the wave from the dipole at top right. A signal will go from it towards point P, also with speed c. But this dipole is an outlying dipole. It is further from P than the dipole on the axis, indicated here. The signal takes longer to reach P from the outlying dipoles than from those near the axis. So, the signal arriving at P from an outlying dipole at any given instant will lag in phase behind the signal reaching P from the dipole on the axis at the same instant. It will also lag the phase of the incident wave reaching P. One can calculate the resultant phase delay in the composite wave from all the dipoles. Perhaps surprisingly, this phase delay turns out to be exactly 90 degrees. The composite dipole wave reaches point P 90 degrees behind in phase compared to the incident wave. This happens to be true for any forward point, not just the one we originally chose. The phase lag will be 90 degrees even if P lies in the next layer. So the two signals go on to the next layer, the incident one, undelayed in phase, and the compound one from all these dipoles, which lags the first by 90 degrees. Clearly, the superposition of these two signals will have a phase delay, though less than 90 degrees. So, the total signal is delayed compared to what would be the case if there were no molecules there. The resultant light wave is delayed by the first layer. In turn, the next layer will delay the light wave, and so on. Its phase proceeds more slowly than through vacuum. The speed of the phase is less than c. And light beams, which are obliquely incident on the dielectric, are bent toward the normal, as we saw before.